Hello students, let's start the mathematical inequalities uh, which will be useful for the preparation of olympiads up to the national and international level. The first one inequality says which is AMGM, arithmetic mean geometric mean inequality. So this is the inequality which you have to keep it in your mind while solving the problems. A1 plus A2 till AN, that will be greater than n times under root A1 A2 product of n number of terms, and square root of n will be there. Okay, nth root will be there. Second inequality is weighted AMGM inequality. Let's suppose P1, P2 be the positive real number satisfying P1 plus P2 plus up to Pn is equals to 1, and A1, A2 till An are non-negative real numbers. Then we will say that their products P1, A1 plus P2, A2 and so on will be greater than equal to up to this condition. It will be equality if A1 is equals to A2 is equals to An. So this is the second inequality which you have to keep in mind. Third one is AMHM, arithmetic mean harmonic mean inequality, which states like this: if a1 a2 till an are positive real numbers, then this situation will hold for a1 is equals to a2 is equals to an. So these three inequalities will play a huge role which you have to keep in your mind. All right. Fourth one is says power mean inequality. See what it does, it really says that if a function, the power mean of order k of a positive real number, that is mk, let's suppose to this kind of situation they have mentioned, it is an increasing function. All right, so this situation will hold. Now let's see, we will see in the questions how we're gonna use this kind of situations for our means. Now the next one is Bernoulli's inequality. It's quite a famous one. 1 plus x to the power n greater than equals to 1 plus rx for this and this situations. So this you have to keep in your head. And some other situations are also there. Do memorize all these things. Next one is Schurz's inequality, which states kind of like this. For any non-negative real numbers ABC, the inequality holds in this situation, for which A is equals to B is equals to C, and for cyclic permutation you can put A is equals to 0 and B is equals to C. For K is equals to 1 you will get a third degree Schurz's inequality which can be written in this manner. These are the following steps. You can write it down all by pausing the video. Okay, alrighty. Now these are some questions we have to solve. So you can see the question number 1. You can pause the video and make the solution by yourself first and then match it with. Okay, what it does, it really says a square plus b square plus c square plus d square is equals to 9 they have given, right? Okay, let me increase the little bit. So we can say a square is this, a will be like this, a square a minus 3 that will be like this, and you can write a cube like this. Similarly we can write b cube 3b square. Okay, c cube less than 3c square, d cube less than 3d square. So therefore we can say a cube plus b cube plus c cube plus d cube 3a square plus b square plus c square plus d square, that will be equals to 27. So this is how we're gonna prove the first question. What does the second question says? 2.2. See, among ABC there are two with the same sign such that you can say BC is greater than 0. So we need to show 2a square plus bc and that's what is mentioned. So you can write it as 2b square minus c. This will be equivalent as in this manner. We can write it down. 2c square minus b plus c greater than equals to 0. b minus c square 2b plus c, b plus 2c, and that is like this. So since 2b plus c, b plus 2c is equals to twice b square plus c square plus 5bc, which is greater than 0. So this equality holds for minus a by 2 is equals to b is equals to c. This equality will hold for any cyclic permutation. So this is how we can prove this thing. There could be another solution also if you want. There could be second solution for this. How we can solve this, I'll show you. The second solution could be like this: 2a square plus bc is equals to a minus b, a minus c plus a plus b plus c, which you can solve a minus b and a minus c as. Similarly, 2b square plus ca is equals to, you can solve b minus c, b minus a plus b, a plus b plus c. When you will solve this, you will get b minus c, b minus a. 2c square plus ab is equals to c minus a, c minus b plus c, a plus b plus c. So when you solve this, you will get c minus a, c minus b. Therefore, you can add, multiply them all like in this manner: 2a square plus bc, 2b square plus ca, 2c square plus ab is equals to minus a minus b square, c square, c minus a square, less than this. This is also another way you can prove this thing. The next question, what it says, 2.3. Please read the question and try to solve it. What does it say? We need to prove like this. Okay, see, the desired inequality is in the format a minus b minus c square plus b, c minus a square plus c, a minus b square greater than equals to 0. So this inequality is clearly true. We can say for the conditions as a this, like this, a plus b greater than equals to 0. So when we replace a by minus a by minus a, what we will get? And replacing a by minus a, we need to show this thing. Okay, so this will involves, we need to show this, and it involves minus a c minus b square plus b c plus a square c a plus b square greater than 0. See, this is true since c a plus b square is greater than 0, and minus a c minus b square plus b c plus a square is minus b times c minus b square plus b c plus a square. Um, okay. Now you can write is equals to b a plus b, a minus b plus 2c greater than 0. So this equality holds for a is equals to b is equals to c. All will be greater than 0. This is how you're gonna prove your 2.3. What does 2.4 says? 2.4 question says we need to, when does equality hold? Okay, see, using the substitution, let's say a is equals to x by root 3, b is equals to x by, no, you should write b is equals to y by root 3 and c is equals to z by root 3. So we need to show x square plus 1, y square plus 1, z square plus 1 greater than equals to 64, right? So this will all will be valid such that xy plus yz plus zx is equals to 9. So what we can do, we can apply the Cauchy-Schwarz inequality, which we can say like this: using Cauchy-Schwarz inequality. So y square plus 1, z square plus 1, that says square plus 1, y plus z square plus, I'm gonna write it down over here, the new format, plus yz minus 1 square greater than equals to x y plus z, uh, plus yz minus 1 square is equals to 64. So this equality holds for xy plus yz plus zx, uh, is equals to 9, and y plus z upon x yz minus 1. That is for y plus z is equals to yz minus 1x, yz minus 1, 9 minus yz, y plus z, y plus z square plus yz minus 1, yz minus 9, y minus z square plus yz minus 3 square into this, y is equals to z is equals to plus minus root 3. So in addition, you can say xy plus yz plus zx is equals to 9 and x is equals to y. We can say xy plus yz plus zx and x into y is equals to z is equals to plus minus root 3. That we can say. So this original inequality becomes an equality for the condition a is equals to b is equals to c is equals to plus minus 1. For this you can say that. So what does 2.5 says? 2.5 inequality. Alrighty. How we can prove this thing? See, we need to this thing we need to prove. Okay, how we can do that? See, since 3 minus 3b greater than 9 by 4 b square, 3 minus 2b square by 4 which is greater than 0, greater than equals to 0, 1 minus 3b, 3b square 3 by 4, 3b square that is equals to 3, 1 minus twice b square 4 that will be greater than 0, 3 minus 5b plus 3b square greater than 25 by 12, 5b plus 3b square is equals to 5 minus 6b greater than 0. It's you can say by using the AM and GM inequality we will have 3 minus 3b b square a square plus 1 minus 3b plus 3b square greater than twice of a under root 3 minus 3b plus b square multiply 1 minus 3b plus 3b square. So now we only need to show that twice 3 minus 3b plus b square 3b plus 3b square is greater than 3 minus 5b plus 3b square. We need to show this. This will be valid only. This will be true if will be true if 4 thrice minus 3b plus b square plus b square is greater than 3 minus 5b 3b square this, which is equivalent to thrice b square minus 3b plus 1 square greater than 0. The equality occurs for a greater than 0 and 3 minus 3b plus b square 1 minus 3b plus 3b square, and you can write b square minus 3b plus 1 is equals to 0. So since a square equal to 1 minus 3b plus 3b square upon 3 minus 3b plus b square, you can solve minus b square plus 3b square 3 minus 3b plus 3b minus 1, and you solve it you will get b square. So this equality occurs for a is equals to b is equals to 3 plus minus root 5 by 2. This will be your answer for this one. Next question you can read as 2.6. What it says, from the identity we can apply twice 1 minus a plus a square 1 minus b plus b square 1 plus a square b square a minus b square 1 minus a square and 1 minus b square. So this will follows that twice 1 minus a square 1 minus b plus b square greater than 1 plus a square b square. This is enough to prove that thrice 1 plus a square b square 1 minus c plus c square greater than twice 1 plus ABC plus A square B square C square. So this inequality is equivalent to thrice A square B square C square minus thrice plus 2AB 3A square B square C plus 1 plus 3A square B square greater than equals to 0. Twice 3 plus A square B square C minus 3 minus twice of AB 3A square B square plus 3 1 minus AB greater than equals to 0. This equality holds for A is equals to B is equals to C is equals to 1. So this is how we can prove this thing. Alrighty, next inequality is 2.7. What it says. See, substituting the ABC by modulus A, modulus B, mod C, and it will respectively the left side of the inequality will remain unchanged, while the right side either remains unchanged or it will get increased. So we are substituting ABC by mod A, mod B, and mod C. So in order to suffice to prove the inequality, we can say P is equals to A plus B plus C, AB plus BC plus CA. Okay. Since Q square minus 3 ABCP is equals to A square B minus C square C minus A square plus C square A minus B square cyclic permutation twice greater than equals to 0 it will be, and we will have A plus B plus C A cube plus B cube plus C cube P cube minus 3P cube plus 3ABC, that will be less than equals to P power 4 3P square cube Q square. So it suffices to show that P square minus 2Q Q P की power 4 3P square Q plus Q square, which is equivalent to the obvious inequality of P square minus 3Q P square minus Q greater than equals to 0. This inequality will hold for A is equals to B is equals to C only. So this is how 2.7 will be done. Kindly read the 2.8 question. Try to solve it, please. Since A square plus B square plus C square to A square plus BC square plus AB minus AC square it will be. So we can write twice B square plus C square also plus B minus C square. This required inequality follows by applying the Cauchy-Schwarz inequality as follows. B square plus C square plus A square. Okay. So how are we gonna follow? BC B plus C plus minus AC B minus C square. And when you solve it, what you're gonna get? AB A plus B BC B plus C CA C plus A minus 2ABC का square. This equality holds when two of ABCs are equal. So this is how 2.8 will be done. Read the 2.91 please. What does it says? 2.9 also for the 2.9 what we can do. See that we can write the inequality as B square plus 1 C square plus 1 A minus B plus C B square plus 1 C square plus 1 square plus A greater than 0. Okay, that we can write. And what is A here? C square plus 1 minus twice BC B plus C square B square plus 1 plus 1. Now you need to show that A is greater than or equal to 0 by the virtue of Cauchy-Schwarz inequality. You can say A is greater than B square plus 1 C square plus 1 twice BC minus 1 B square C square plus B minus C square greater than equals to 0. So this equality holds if b square c square plus b minus c square is equals to 0. Only if this b is equals to c is equals to 0, the original inequality will becomes a square plus 1 greater than 0, which will be strictly obedient, strictly follows. So what does it says for the 2.1010? What does it says now? See, among the a square, b square, and c square, there are two either less than or equals to 1 by 4 or greater than or equal to 1 by 4. Let b square and c square be these numbers such that 4b square minus 1, 4c square minus 1 greater than 0. Now we can say 16 by 5, b square plus 1, c square plus 1 is equals to 5 times 4b square minus 1 by 5 plus 1, 4c square plus 4c square 5 plus 1. 5 times 4b square minus 1 by 5, 4c square minus 1 by 5 plus 1, equal to 4b square 4c square plus 3. It's sufficient enough to prove that a square plus 1, 4b square 4c square plus 3, that will be greater than equals to a plus b plus c plus 1 square. Okay, write this, and I'm now writing this inequality as a square plus 1 by 4, 1 by 4 plus 1 by 2, 1 plus 4b square, 4c square plus twice, a plus b plus c plus 1 square. We recognize the Cauchy-Schwarz inequality here. So this is how it will be done. Thank you.